Today we will see the crystalline direction and plane in the today lecture. So that is Miller indices, plane and direction. See, when you go for any crystal, you have a n number of possibilities for choosing a unique cell, right? So that convenient representation to identify the particular direction or plane in the unit cell is the concept is Miller indices, plane and direction procedure. Okay, here in this slide you can see it is a parallelepiped is shown here for the particular unit cell. It is shown here with inclined with the angle. That is a cube that is inclined with the some angle. You can see here. So you have axis of x, y and z. Right? You can see here. These are the edges. This is considered this is the origin. That is 0. This is the edge with the length of a. For the y with the length of b. For the z the length of c. We can see that the corresponding angle it can be the inclined can be determined with the terms of alpha, beta, gamma. Based on that the structure will be defined. The 2D or structure or 3D structure it is defined based on this inclined angle, right? So now let me detailedly explain about what is the procedure to identify for the particular direction. Here I am given one arrow. This is a interest that this is the direction I want to find for this vector. Okay, this is the direction I want to find. Okay, you have n number of direction, but in order to make you to understand, I have taken this arrow. This is a vector which this is my choice. The direction is given in terms of vector. Okay. So what is the procedure? Let me say the first procedure, you want to choose a point on the direction as a origin. Okay, the second is a choose a coordinated system with axis parallel to the unit cell edges, and third is a find the coordinates of the another point on the direction. That means first point is choose a point on the direction as a origin. So this is the direction. That means I want to choose this as a origin. Okay. From that position only I want to put the direction. See, the choose a point on the direction as origin. So this is my direction which I was interested to find it, right? So here I have given the origin 0. Second, choose a coordinate system with axis parallel to the unit cell edges. So this is the unit cell edges. So here you can see the edges are x, the parallel edges are x, y and z. Okay, the third is find the coordinate of the other point on the direction. Okay, you want to find the other point coordinate on the direction with respect to the vector which you are interested to find. When you put for here, see here this is a point I set. So that means I want to this coordinate will be 1. Okay, with the edge coefficient of 1a. Similarly, when you go for b 0, here I am not interested, right? That is the third step. Here it is given here. So that means it is 0 b, right? You have a 0 b, right? Then if you see the z axis, here also that is 0 c, right? 0 c, this is b. So the a, b, c are coefficient. So when you represent for the Miller indices for the direction, so you should use the notation because you should be familiar with the notation when you are representation. So generally you have a direction, plane and also have a family. Okay, we used to say the family of direction or family of planes. So you have a 4 rotation generally. When you put for any any direction, it should be represented by the square bracket. Okay, here I will show you. So you should use this. Okay, this is a notation you have to use for the direction. This is a notation you should use for the plane. Okay, so for the direction of family of direction, this angle bracket, the floral basis for the family of planes. So here, that means we are doing the direction analysis. So that means you have a square bracket 1 without including the coefficient 1 0 0. So just given the example, right? So this is the procedure for any direction. Okay, this is the 3 procedure which you want to use to find the Miller indices for the direction. When you go for plane, so this is a plane. Okay, this is a plane. So this is a plane for the particular unit cell. Okay, so if you take this is a unit cell from here, so this is a plane. Okay, so first what you want to do is, first you want to express the intercept. That is the first procedure. The intercept means for x-axis and y-axis, for z-axis you have some intercept. So intercept is very important. So you want to identify the intercept. Then you want to take the reciprocal for the intercept. Consider like a 2 1 2 means that is the intercept. Here you can see here 3 1 2. That means the reciprocal for the intercept is 1 by 3, 1 by 1 and 1 by 2. Right? Then you want to reduce the reciprocal to the simplest set of integer. Before that, what you want to do is, you can like a third and fourth subset more common. So what you want to do is, you want to multiply it with your common factor. So that is a LCM value. So here I can take, here you can see 3 1 with the coefficient, it was the present 3a 1b 2c, and the reciprocals are 1c 1 and 1 by 2. Okay, so I will multiply with the 6, that is the LCM for this factor. So 3 divided by, I am just multiplying with the least common factor. 6 by 3 2, 6 by 1 6, and 6 by 2 3. So that is a Miller indices for the particular plane. Okay, now you understand how to find for the plane and indices. I hope you understood, right? So first procedure is, we want to intercept, you want to express the intercept with the coefficient of a, b, c. Then you want to take the reciprocal for the intercept. Then you want to reduce the reciprocal in the to the simplest set of integer HKL. Finally, you will be representing the HKL. Before that, you want to multiply with the least common factor value. That is represented by HKL. Okay. So another thing important is, when you are representing the negative side. See, let me explain. So this is your center point. Okay. So this is your x. Let me take. So this is your y. Okay. This is your z. Maybe the plane or direction will be in this direction also, right? So that is can be represented by minus y. Similarly, here will be in this direction also, minus x. Minus x. Similarly, here also, down also, right? So if you understand this concept, you can find for any direction and planes. I have just given some examples. Okay, so here you can see here, this is given for the direction along the edges of the cube. Along the edges of the cube. Along the edges of the cube means this edge. Along the edges of the cube, the directions are specified. So 1 0 0. So it is along the x-axis. So other will be 0 0. So infinity. Okay, so there is no position of y and z. Similarly, when you go for this direction, x is 0 and z is 0, 0 and 0. Similarly, 0, 0, 1. Similarly, here it is in the minus direction with respect to the y axis. So 0 is x, y is minus 1. So when you are putting a minus 1, you should not put like this. So you want to put like a 1 bar. It is equivalent to this. Okay. It is also mentioned in the PPT also. So if intercept at the infinity, the corresponding index is 0 and negative values should be quoted with a bar over. So that's what explained here. Similarly, when you want to represent the like a family of direction, right? When you want to represent the family of direction, you should use this angle bracket I said earlier, right? That means what is a possible direction? See, you know, if you have a cube, you have a 6 possible direction. That is 1, 0, 0, front, back, front, back, front, back, for totally 3 phases. You will be having 6 opposite and front ends. Similarly, when you go for this is with respect to the diagonal direction in the cube. So totally you will be having 8. 1, 2, 3, 4, 5, 6, 7, 8 diagonals. Right? So you have a 8 representation of direction. Right? 1, minus 1, 1, minus 1, minus 1, 1, 1, 1, 1, minus 1, 1, 1, 1. With respect to the position, it was plotted. So this is respect to the plane. Okay, in the last slide we have given with respect to some examples. We have seen with respect to the direction. This is with respect to the plane. So what is the procedure? First you want to see the intercept. So for the x-axis, it is in the center, not in the full. A is a half, that is 1 by 2. Right? It is 1 by 2. So 1 by 2. Right? 1 by 2. So next, what is a y? Y, that is full 1. Right? 1. And z also 1. Then what you want to do? You want to take a reverse, that is 1 divided by 1 by 2. Then 1 by 1, 1 by 1. You want to multiply with the 2, correct? That is a least common factor for this values. So 2 by 2, 1, 2 by 1, 2. Then you will be having, sorry, here z is 1 by 2. You can see it is in the half, the mid half. So this is also 1 by 2, right? This is also 1 by 2. Okay, that means 1, when you take a reciprocal and multiply with the 2, you will be getting 1 comma 2 comma 1. This is a final representation for this plane. Similarly here, this is for front plane for the cube 1, 0, 0. This is for top plane. This is the top 0, 0, 0, 1. And this is for like a inclined in the center angle. This is inclined in the center part of the diagonal. It is 1, 1, 0. Similarly for this inclined in some position with respect to the x and y. So you can see in x it is in the mid of 1 by 2. In y it is in the y complete 1, and z it not touching, that is infinity. So that means 1 divided by 1 by 2, 1 by 1, then 1 by infinity. Right? So you want to multiply with the common factor. So same procedure, you will be finding the value for the Miller indices. Okay, you will be getting 2, 1, 0 for this.